Information security is an encompassing discipline that protects an organization's entire data footprint, encompassing computer hardware, digital software, and physical paper records. Significant breaches often occur entirely outside the digital realm, such as when firms accidentally dispose of confidential customer records in the regular trash. To secure data, we rely on the CIA triad: confidentiality, integrity, and availability. Confidentiality protects information from unauthorized individuals. Integrity ensures data accurately reflects business events, preventing malicious modification. Availability guarantees authorized users can access resources whenever needed. If any single pillar of the triad fails, the entire system is compromised. Security must therefore be addressed simultaneously across every level of the enterprise. Translating these theoretical goals into practice requires a formal 5-step information security plan. Steps 1 and 2 identify threats and determine risk. On this matrix, sabotage plots high for potential damage, but low for likelihood. Steps 3 and 4 design targeted controls based on these risks, integrating them into an enterprise-wide plan. The 5th and final step enforces this plan by establishing strict system access policies directly tied to individual job duties. This creates a defense in-depth matrix, a series of overlapping layers moving from macro-organizational governance down to the microprocessing of a single transaction. The outermost layer of this architecture consists of systems development controls. Security begins with governance, specifically through a dedicated steering committee. This committee includes managers from both IT and end-user functions, who approve development projects, allocate resources, and ensure all new systems align with the organization's strategic plan. Within the development process itself, the most critical control is the separation of duties. A strict barrier exists between personnel. Programmers who write the code cannot be the computer operators who run the production files. When existing systems require updates, change management protocols require that programmers work on separate copies rather than live production code. These changes must be tested using incorrect and non-ideal data to ensure the program handles errors safely before it is deployed. These development controls serve as the bedrock of the system. Without governance and separation of duties, a programmer could implant a logic bomb that bypasses all subsequent software defenses. Moving one layer inward, we reach the operational perimeter, beginning with physical controls. Restrictions range from simple guard desks and entry keypads to biometric scanning technologies that use unique retina patterns or monitor keystroke dynamics. Closely related are environmental controls, which protect hardware from physical destruction. Processing facilities require constant temperature and humidity regulation, alongside advanced fire suppression systems. These controls protect the availability pillar of the CIA triad. Data remains inaccessible if the physical servers are stolen or destroyed by heat. The digital side of this perimeter is defined by logical controls. These function through authentication, verifying who a user is, and authorization, dictating what that user is allowed to do. To combat password fatigue, which often leads users to write down passwords in plain view, organizations use single sign-on systems to manage credentials across multiple IT resources. Authorization is enforced through role-based permissions, ensuring access levels match the human organizational chart. For example, an accounts receivable clerk is authorized to view customer credit limits and adjust balances by entering invoices. However, that same clerk is blocked from updating the master balance file. That specific capability is restricted to the department head. By mapping digital permissions to job duties, logical controls reduce the threat of internal data theft or sabotage. At the core of the architecture are application controls, which protect data during daily operations: input, processing, and output. Input controls act as the gatekeeper, ensuring that all data submitted for processing is authorized and accurate. Online inputs use edit checks to prevent incorrect data types, like letters in a number field, and limit checks to flag unusually large transactions for supervisor approval. To prevent transposition errors during data entry, systems use a mathematical algorithm to create a check digit, which validates serial identifiers as they are typed. For large groups of data processed at once, the system uses batch input controls. This includes the hash total, a sum of numeric fields with no inherent meaning, like social security numbers, calculated purely to verify that every record in the batch was processed. These controls are the primary defense against the most common threats to integrity: human error and input manipulation. Once data enters the system, processing controls built into the application code take over. The system performs validation by cross-referencing identifiers against master files, such as verifying that a vendor number exists in the authorized database. Arithmetic controls, such as zero balance checking, ensure that the debits and credits in a transaction sum exactly to zero before processing continues. Finally, output controls verify that the entire processing cycle was complete and accurate. This relies on a detailed audit trail, which records batch numbers, submission times, and the total number of records or dollars rejected during the run. These final pipeline stages serve as a failsafe. Even if the perimeter is breached, internal mathematical checks are designed to flag and log the anomaly. This completed architecture shows how multiple security layers function as a single interlocking system. Every layer is designed to uphold the CIA triad: confidentiality, integrity, and availability. The redundancy is intentional. If physical security fails and a laptop is stolen, logical controls like encryption protect the data's confidentiality. If an internal user attempts to bypass their authorization, application-level processing controls are there to defend the data's integrity. Effective security requires this systematic interlocking blueprint. By stacking internal controls into overlapping layers, an organization creates a structure capable of detecting and containing threats across every stage of the data lifecycle.